facts about improper integrals that are worth committing to memory, even though on regular exams you may use a note card. First fact that's worth knowing is that if you integrate some constant over x to the p power from some fixed positive number, last time we used the number 1, that's the most common thing to use, but here I'll use an arbitrary positive number, I'll call it a, to infinity. So where a is positive, c can be any number. C is an arbitrary real number. That's notation that means C is an element of the real numbers. And P, well, technically P can be anything in what I'm about to say, though most typically when we write such a function with the x to the p power in the bottom, we do typically think of P as positive. That's the way we're suggesting to write it. We could think about negative values of P, but then we're really not thinking about reciprocals of powers of x in that case, reciprocals of positive powers of x. So most typically we're imagining P to be positive. This converges if P is actually bigger than 1 and diverges if P is between 0 and 1, including the case where P equals 1. Okay, we derived this last time. Remember, these improper integrals are computed by using a limit. We write an infinity up there initially, but because there's an infinity, we call it an improper integral, meaning it's not a proper ordinary integral. It's somehow a new kind of integral. It's not a true integral in the usual sense of chapter 5. It's a limit of such integrals, where if we replace the infinity with a b, we would let b go to infinity, which just means it's just shorthand for saying b gets arbitrarily large without bound. We're not literally thinking of infinity as a number. At the other extreme, if I integrate the same kind of function here with these exact same assumptions, well, okay, these assumptions all apply to this one. I guess I'll go ahead and use the letter A here still. These exact same assumptions are going to apply to this next one. But I'm going to go, instead of from A to infinity, I'm going to go from 0 to A. I was thinking I wanted to use the letter B here instead of A, since B is a more common letter for the upper limit of the integral, but it's not a big deal if I use the letter A. Why is this improper? When P is positive, this is improper because you'd be dividing by 0 at x equals 0. It's got a vertical asymptote, in fact. The graph of this has a vertical asymptote at x equals 0. The y-axis is a vertical asymptote. You don't see an infinity symbol, but the graph is going up forever and ever. I'm wondering, does that region still have finite area, even though it has infinite extent, even though it goes up forever and ever? And the answer is yes, it can have finite area. It converges if P is between 0 and 1, and diverges if P is greater than or equal to 1. Notice that in both of these situations, it diverges if P equals 1. P equals 1 is the case where the antiderivative is natural log. And we know the natural log function not only goes up forever and ever without a horizontal asymptote, although it goes up slowly, it goes down forever and ever. It's got a vertical asymptote at x equals 0. The limit as b goes to infinity of natural log of b is infinity. And the limit as a goes to 0 from the right of natural log of a is minus infinity, though we needed those limits in class last time. That's why in the case where P is 1, you get divergence in both situations. because the antiderivative involves natural log. It's also worth knowing and taking to the bank that if you integrate an exponential decay, well, an arbitrary constant c times an exponential decay, let me write it like that. C is any real number. K I'm taking to be positive. And A can actually be any real number here. If I integrate this from A to infinity, if I do that improper integral, this converges. That's worth knowing as well. Exponential decays have the x-axis, y equals 0, as a horizontal asymptote. And in fact, they go to that x-axis so fast that you get convergence. We didn't prove that last time. Let's go ahead and prove it this time. Let's do this as a calculation. It's a limit as the upper limit b goes to infinity of the integral from a to b, c e to the negative kx dx. When you do the integrals, when you're trying to decide whether it converges or not, at least in section 7.6, you should compute a limit. Actually, improper integrals come up in 7.7 as well, but we're not computing limits in that section. We're using a test called the comparison test, and I am going to talk about that in a few minutes. But how do you do this limit? Well, as far as the limit sign goes, just carry it along for the ride until the very end. You're hoping at the very end you'll be able to take the limit. Antiderivative of this, if you're careful and you're guessing, you'll see it's negative c over k e to the negative kx. Right? You can check it by differentiation. When you differentiate that, the chain rule gives an extra factor of negative k that will cancel with the negative sign and also the k in that denominator. A lot of letters, but if you keep your wits about you, you can do it. That's the fundamental theorem of calculus is what I use right there, FTC. Now I'm just simplifying. Simplify. Plug in x equals b like this and subtract what you get when you plug in x equals a. Making a pretty complicated looking expression that I'm going to rearrange a little bit. I'll factor out the c over k and write what's left like this. The two minus signs, by the way, make a plus sign. Those combine to give a plus sign there. And if the limit exists, I can factor out the c over k. I'll go ahead and do that just for the sake of clarity. Assuming the limit exists, I can write this. Does this thing have a limit as b goes to infinity? Again, keep your wits about you. The c, the k, and the a are all constants. As far as the limit is concerned, that's what's changing, the b. What happens as b increases? The fact that k is positive means this part goes to 0 as b goes to infinity. Since the k is positive, so negative k times b is negative. And in fact, getting more and more negative as b gets larger and larger positively. Definitely going to 0, in fact, pretty rapidly. You can now replace that with 0, take the limit. The limit sign goes away. You simplify a little bit, you get c e to the negative ka over k. Kind of a still complicated expression for this limit, but the point is, it's a number. A number. It's not infinity. So this means the improper integral converges. to that kind of complicated looking number. This justifies the statement.